Hi, this is an introduction to the first week's worth of material for the module Discrete Mathematics. There will be 11 weeks in all, and these correspond to the 11 chapters of the lecture notes and the 11 sections on Keats. So the material for week one will be, I'm sure, familiar to many of you, or most of it will be. There are 4 subsections and there'll be a lecture clip for each of them. But I think you'll find the newer material is in section or subsection 1.3 and 1.4. In the first segment, 1.1, I shall talk briefly about summation and mention the notion of proof by induction. But since I'm sure this will be familiar to everyone, I thought it was appropriate to actually use what I said about this last January. So here goes, and please contact me if you have any questions.
And let me just give you an example. Here's a typical example, very elementary example, you probably had it before. Prove that the sum of the first n odd numbers is, does anyone know what it is? Sum of the first n odd numbers. Well, yeah, it's n squared. You know, 1 is 1, 1 plus 3 is 4, 1 plus 3 plus 5 is 9, so it's fairly clear you're going to get n squared. Now, lots of ways of doing this, but let me just sort of write this out in different ways. So the sum is, so this is a sort of exercise, for example, the sum that we want, let's write it down in symbols. So it's 1 plus 3 plus 5 plus etc. And we need to go up to the nth odd number. And we have to work out, how do we write the nth odd number? And the answer is, if you think about it, 2n minus 1. That is the nth odd number. You just I mean, it's going to be something like this. It might be 2n plus 1, but you check this because when n is 1, it's 1, which is correct. So when n is 2, it's 3, which is correct. So that's the sum we want. So if you do analysis, you might want to convert that into a sigma notation. So that's the summation from j, say, is equal to 1 to n of 2j minus 1, because each odd number has the form 2j minus 1. And then if you like manipulating things, you'll say, well, I can simplify that because this is all linear. That's twice sigma j from 1 to n. And then you have to be careful. It's not just minus 1 full stop. We've got sigma minus 1. We've got n terms here, so it's actually minus n. So that's the same number. Now, you might already know, even if you didn't know the sum of the first n odd numbers, it's more likely you know what the sum of the first n numbers is. Who knows what the sum of the first n numbers is?
n plus 1 over 2.
It's a half n into n plus 1. I thought most of you would know that. So, of course, that's as difficult really as the original problem, but you're more likely to know that. So if you do know that, if known, we can use that and finish the problem, because we get this, and so it's n squared plus n minus n, that's equal to n squared, so that's correct. So that's one method, that's sort of method 1. Okay, so that's method 1. Method 2. Method 2 is going to be induction. Okay, so how would you do this by induction? It's all very easy. But just to remind you, you say, now I'm going to write it out a little informally. If I presented this work to the Cale Dixon. I'm not sure he would give me full marks, but anyway, I'm going to write this down informally. Let's write down our induction hypothesis. So let's assume that the result is correct for a given value, say n. So let's assume that our sum of the first n odd numbers is indeed n squared, and let's try and prove it for the next value of n plus 1. Okay, first of all we have to check that this is correct at the beginning. Okay, and it's okay, this formula is correct, it's okay for n is equal to 1 or 2. Because when n is 1, we just get 1 is equal to 1, which is correct. So it's correct, I shouldn't say okay, that's too informal. It's correct for n is equal to 1. So we now want to look at the sum of the first n plus 1 odd numbers. So for n plus 1 odd numbers, we're assuming this result. So what we have is 1 plus 3 plus 5, and we're going all the way up now. We have the nth odd number, and then we're going to add another one, so that would be 2n plus 1 minus 1, which is the same as 2n plus 1. That's the n plus first odd number. And what is that? Well, we already know by hypothesis that all this stuff is n squared. That's the induction hypothesis. We can assume that. Okay, so what we have, therefore, is that the whole lot is equal to n squared plus 2n plus 1, and that's exactly what we wanted, because that's n plus 1 all squared. So that's correct. That means that the induction proceeds. So the induction proceeds and the proof is complete. The only thing I get a little confused about is how to write this out properly. And if I were being very formal, I'd need a different letter n if I assume the hypothesis is true for maybe m and so on. But I think it's fairly clear what I've written here, that this is a proof. For me, this is fine. This is proof by induction. So that's the second method. Is that clear? And I didn't need to know this result about sigma j. I didn't need to know. That was, if I knew that, I had this other proof, or if you like using summation signs, you might prefer the other proof. I'm going to give you a third proof, which is my preferred proof because I'm a geometer. So here's the third proof. And I'll illustrate it for n is equal to 3. Well, the first 3 odd numbers. I'm just going to draw this picture of a square divided into 3 and divided into 9. And that is, of course, there are 9 little squares. And you see, that is, I can divide it like this. There's 1 plus 3 plus 5. Okay, so this picture is illustrating 1 plus 3 plus 5 is equal to 3 squared. And that is, in my view, a proof. Although I've only done one case, anyone who looks at this picture will understand that if I now add, if I have a 4 by 4 square, I've added on 7. And that will be 4 squared. Okay, so this, in my view, is a proof. You might not agree, but I think this is a proof. I haven't written down the words. You know, I should write down therefore in general, and you can make it rigorous. But the question is, does this picture convince you of the general result? And in my view, it does. So I regard that as valid. Okay, that's all I'm going to say about induction. If you're not familiar with induction, look at the notes, and there will be other examples on that. There will be quite a few examples on sheet 1 to refresh your practice in the proving things by induction. Sometimes you have to prove something by induction by assuming a slightly more general hypothesis that the result is true for all integers less than a given one. So if you want to prove that any number can be factored into primes, you have to use what's called the second principle of induction, in which you assume the result is true for all numbers up to n, not just the preceding one. You don't do one step at a time, but you assume the result is true for all numbers up to n. So that is sometimes needed. And another hitch is that sometimes you need to check two initial values. You always need to check something at the beginning. In some cases, you may need to check more than one initial value, but you'll see that in the problems that arise.